Hello everyone. So today we'll be having the last session for this course, and this is a course in statistical mechanics that I had been taking as a part of my PMRFTship. I am Sauravi, a PhD student here at IISc, and so in this course we had started with thermodynamics, then we spoke about the probabilistic approach, how we got towards the ensemble theory, and from there we tried to link the microscopic and the macroscopic pictures, and then gradually moved towards quantum statistics, where we used the density matrix formulation, and we tried to see how, based on what kind of particles we are dealing with, whether they are distinguishable or indistinguishable, whether they are fermions or bosons. Based on all of that, their distribution into different energy states differ. Okay. And that also manifests as different, phenomena happening at the macro scale. So the pressure, the temperature, or you know all these expressions depend on how this microscopically how these particles get distributed into different energy states. So we discussed all of that, and in today's class what we'll try to do is we'll try to recap and revisit all that we have been doing throughout the course as a revision. Okay, so so as to summarize whatever that has been tried to be covered in the course. Okay. um, so let's get started. So I will discuss some problems even here, but these problems had already been discussed before, and it will be more of a recap where we'll try to highlight some of the interesting or important questions, and you know, and those will be useful to actually link the entire, story of how the course proceeded. So most of the questions that we'll be discussing, or almost all of the questions that we'll be discussing today, if, as well as the concepts, they're all has been already discussed at some point in the class, and we are trying to recap. Okay. Okay. So we did start our course with thermodynamics, which is a macroscopic description. And if you remember, we said that macroscopic means you are looking at the system as a whole in a way. So you can define the temperature or the pressure or the volume. All these things are macroscopic descriptions. While the microscopic description would be the position or the momentum of the individual particles. Okay. So all of that is the microscopic picture. And a major part of statistical mechanics is bridging these two descriptions. So we started with the macroscopic description, where we tried to see how there are different laws of thermodynamics which hint at different, phenomena macroscopically, and tries to explain different systems. And we discuss the major laws that comes out of thermodynamics. So we started with the zeroth law, which says that if you have two systems A and B, and they're separately in equilibrium with a third system C, then they're also individually in equilibrium with each other. And while this seems to be pretty trivial, but it's actually not, because it has a huge significance, because this gives rise to this very idea of an important state function called the empirical temperature. Okay. And that lies at the very heart of thermal equilibrium, right? So we say that two objects are in thermal equilibrium when their temperatures are the same. So this very idea of state function, what do you mean by state function? So there can be functions which depend on how you reach to a point, okay? And there can be certain functions which just depend on the current state, okay? So the the variables which do not depend on how you reach to a certain state, but rather just the state itself, are state functions. Okay. And temperature is one such important state function that comes out of the zeroth law. Okay. Then we went towards the first law, which discussed about, the basically the conservation of energy in a way, which says that if you have a certain heat, you know, given to a system, a part of it will be used to increase the internal energy of the system, and the rest will be used to do some work on the system, right? So based on whatever system you're talking about, the expression for work can vary, right? So you can have a, if it is an hydrostatic system, then you can say that there's certain pressure and you do there's a volume change associated with the pressure. So then the work done is given as minus PdV. So similarly, if you have some other systems, if you have a tension for a string, then you would say that if F is the force or the tension applied to the string and the length in change is given as dl, then FdL is the work done, right? So depending on whatever system we are talking about, the expression for work done can vary. Okay, and it is important to note and remember that you do have uh, the so you can see this cut on the differential, right? So this shows that these are inexact differentials, which means that they depend on how you do the process. Okay, these are not state functions. While this term here, the internal energy, is a state function. So the first law talks about this state function of internal energy, which is independent of how you reach to a certain state. It is just a function of the state itself, while the work done and the heat absorbed or released, this heat and work done, these are inexact differentials which depend on the path that the system takes to go to a certain state. Okay, so this is the first law. And then there comes the second law. So each of these laws, as you can see, is giving us new state functions. The 0th law gives us the temperature. The first law gives us the internal energy. The second law gives us a very fundamental, important quantity or a state function called entropy. Okay, so basically from the second law, we get an idea about, what is the natural tendency of a certain state, a certain system as it, what do I say? So as it evolves with time, right? So if you have a certain system, we by this time already know that a system tries to maximize its entropy or it tries to minimize its energy, right? So this direction of time, okay, comes from the second law of thermodynamics. So here there can be multiple statements. So the Kelvin statement says that there cannot be any process whose sole result is the complete conversion of heat into work, which means that if you have some engine and then you want to, convert some heat into work, it will not have 100% conversion, right? Some of the heat will be sent back to some sink. Okay. So you can define the efficiency of this engine in terms of what is the work done by what is the heat input from the source. And this is always less than equal to 1. So like it cannot be 1. There cannot be complete conversion from heat to work. Okay. Some of it will definitely go to the sink as heat. And then, quite equivalently, you can also have another statement which says that no process is possible whose sole result is the transfer of heat from a colder to a hotter body. So it is talking about the direction of flow of heat, right? So it is saying that if you have a cold object, you cannot extract heat out of it and just, give it back to some hotter body. You have, for this to be done, you need to do some work on the system. Okay, so this is like a refrigerator. So if it has to extract QC amount of heat out of a colder body and send it to a hotter body, then there has to be a W work done on the refrigerator, where the efficiency is given as QC by W, where QC is the heat extracted from the colder body and W is the work done, right? So it's just the basic concept is the same, and it gives us an idea about direction of flow of current, direction of flow of, how a system evolves normally, right? So from the second law, we do get to this theorem called the Carnot's theorem, which actually introduces us to an engine, which says that if you have some engine, okay, and it's running reversibly in a cycle, okay, between two temperatures, okay, so you have a QH, okay, a source temperature, and a sink temperature QC. Okay, so QH is greater than QC. And then you have an engine which is working reversibly in a cyclic manner between these two temperatures. Then one can define, so basically this is how the, engine works. So there's a isothermal expansion followed by an adiabatic expansion. Then you have an isothermal compression, and then there's an adiabatic compression, right? So this is a cyclic process, right? So now it says this gives rise to a theorem which comes from the second law, which says that no engine operating between two reservoirs at these two temperatures, TH and TC, is more efficient than a Carnot engine operating between them. So what it means is a reversible engine working in a cycle between these two temperatures is the most efficient one. Okay, that's the Carnot theorem. And from there, you can also get to this very idea of entropy, which comes from the Clausius theorem, where it says that for any cyclic transformation, reversible or not reversible, you can define a quantity. So if you say that dq is the heat increment supplied to the system at certain temperature T, then the closed integral, because you're having a cyclic transformation, right? So closed integral of dq by T should be less than equal to 0. Okay, and it becomes equal to 0 when you have a reversible system, and otherwise it would be less than equal to 0. And from there, you can actually define this quantity called entropy, which says that if you have a reversible process going on between two states, A and B, okay, where it's a reversible system, reversible process. So dq is the heat increment during this reversible process, and T is the temperature, and you're going from point A to point B, then this quantity here, so dq by T integral from A to B, is entropy. Okay, it's a state function which just depends on the two states, A and B. It doesn't depend on how you are going there. Okay, and from there you can actually rewrite the first law. So you can write, so this is nothing but the first law of thermodynamics, but now you can replace dq as tds, and again dw can be written as summation over I ji dxi, where ji is your generalized force, dxi is your generalized displacement. So based on the system, your force and displacements, like the generalized force and this generalized displacement, can vary. Okay, but the important point is that now if you have a irreversible system, you get this term here, which says that, for a isolated system where you can set dq to go to 0, ds will always be greater than equal to 0. So this is telling you that for isolated system, entropy always tends to maximize as it approaches equilibrium. So this is talking about the, natural, temporal evolution of a system, which always tries to maximize its entropy. Okay, that comes from, this very idea comes from the second law of thermodynamics. Okay, so the zeroth law gives us the state function called temperature. First law gives us a state function called internal energy, and the second law gives us a state function called entropy. Okay, now you can also define different response functions. So when you have a system, okay, how is your system responding to different changes in different, macroscopic variables? What happens when you change temperature? What happens when you change pressure? Right? So that's how the response functions are defined. So you can have different response functions like the specific heats, like here. So it says dq dt at constant volume, which tells us how much amount of, if you add certain amount of heat, what is the temperature change associated with the heat input, right? At a constant volume. Similarly, you can have specific heat at constant pressure. So these are all response functions. Again, you can define quantities like compressibility of a gas, where it is given as minus del V del P at constant temperature by the volume, right? So so here you can see it's an isothermal, during an isothermal process, if you change the pressure, how much is the change in the volume? That can be quantified from this quantity called the compressibility of the gas. Right. Similarly, you can define expansivity of the gas, which is given as del V del T at constant pressure by volume. So here, that means here you're keeping the pressure constant and you're varying the temperature, and you're trying to see how much is the volume change in the gas. Right. So that gives you the expansivity of the gas. So these are all response functions, which one can also, explicitly measure. So you can measure the expansivity of a gas or a compressibility of a gas by looking at how these variables change. Right. Or you can measure the specific heats. So these are response functions that define the response of your system to changes in different thermodynamic variables or macroscopic variables. Now, one can have different kinds of polytropic processes. So one of them is the adiabatic process, where you have the net heat exchange is set to 0. And in that case, you have this relation, which is given as Pv to the power gamma equal to constant, where gamma is the ratio of the specific heats. Okay, so gamma is given as Cp by Cv. And you can also rewrite the same expression in terms of temperature volume or temperature pressure. But these are all, this is like an example of a typical polytropic process, okay, which comes up when you have, for this case, like adiabatic process, which comes up when there's no heat exchange. Right? So you can have all these different expressions. Now, based on what kind of process you are dealing with, your expression for heat absorbed or your expression for work done would vary, because work done or heat, these are all inexact differentials which depend on how the process is happening. Okay, while the internal energy change or the entropy change, these do not depend on whatever process you are following. Okay, these are just state dependent values. Now, if you want to describe a system, now you can define different thermodynamic potentials, okay, based on whatever system you are dealing with. So if you have a system where there is no heat exchange and the system comes to some mechanical equilibrium with a constant external force, then you can define a potential called the enthalpy, which is given as H equal to E minus Jx. So J is the generalized force, X is the generalized displacement. So for a hydrostatic system, you would write H as E plus PV. Okay, so there J is given as minus P and X is given as V, the volume. Okay, so then you can define a quantity enthalpy given as H equal to E plus PV in that case, and that would be a thermodynamic potential, which would also give us an idea about how the system is trying to approach to equilibrium. So for a system like this, you would say that as the system tries to approach equilibrium, delta H will it will try to minimize delta H. Okay, so delta H will be less than equal to 0. Okay, similarly, if you have a system where there are isothermal transformations going on in the absence of a mechanical work, so dW is 0. In that case, you can define the Helmholtz free energy as your thermodynamic potential. And you can say that as the system progresses towards equilibrium, it tries to minimize the Helmholtz free energy. Similarly, now, if you have another system, another process going on where, there are isothermal transformations involving mechanical work at constant external force, then you can define the Gibbs free energy, which is given as G equal to E minus Ts minus Jx. And you can say that as the system approaches equilibrium, it tries to minimize the Gibbs free energy, right? So just like a system tries to maximize its entropy, it tries to minimize its, free energies or minimize its enthalpy. And you can choose this different thermodynamic potentials based on whatever system you are dealing with, whatever process your system is undergoing. Accordingly, you can choose your potentials and you can use them to describe your system, describe how your system is approaching equilibrium or whether it's in a equilibrium state or not, all of that, right? So that's how you can use these different potentials. Now, there are very fundamental relations called the Maxwell's relations that try to relate how, the different macroscopic variables, okay, how they vary during different processes, okay? So these are very fundamental for Maxwell's relations. Now, it has a lot of significance. I mean, you can see in a very, general way, if you want to describe a system or characterize a system, or say that with what is happening to the system, if you want to quantify that, you quantify it in terms of certain measurables, right? You can measure its pressure, its volume, its compressibility, its expansivity, or you can measure the specific heats. So these are certain things that you can measure directly, okay? But then if you are asked to measure, suppose this quantity, what is the del P del V at constant entropy? Explicitly keep it, like how do you keep entropy constant, right? So, I mean, these are not directly measurable quantities, okay? These are useful quantities, but directly, explicitly measuring them in an experiment is difficult. So what you can then do is basically you can try to write the same expression, okay, same quantity in terms of other variables which you can directly measure. So you can measure the change in volume with temperature at constant pressure. You can measure the change in pressure with volume at constant temperature. You can measure the change in temperature with pressure at constant volume. So these are all variables that you can directly measure. Okay, you can measure the specific heats. You can measure the temperature. So you can measure all of that. And now using the Maxwell's relations and the cyclic relations, you can basically write this quantity in terms of all these directly measurable quantities. Okay. And that's one of the major uses of Maxwell's relations, where you can actually relate certain quantities in terms of directly measurable, quantities, right? So that's how you can use them. Now, Maxwell's relations also find a lot of implication directly in understanding how, different phase diagrams for different substances work. So, and how do you get to the, Maxwell's relations? So you can use the different thermodynamic potentials to actually derive the different Maxwell's relations. Okay. So like here, these are the four. So internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Now from here, what you can do is you can directly try to write the differentials, okay, explicitly. And this is what you would be getting, right? Now from here, by looking at, or writing this explicitly in terms of the partial derivatives involved, and then comparing the expressions would give you a way of deriving the different Maxwell's relations. So for an example, if you take the first, this expression here, so you can say that now if you write du in terms of del u del s at constant volume, ds plus del u del v at constant entropy dv, then you can say that just by comparing this with the explicit expression for the differential, you can say that del u del s at constant volume is given as T, and del u del v at constant entropy is given as minus P. Right? Now, at this point, you have to use the fact that your internal energy is an exact differential, which means the order of derivatives do not matter. Right? So what you can say is you can say del square u del v del s should be equal to del square u del s del v. And from here, you can now say that del T del v at constant entropy is same as minus of del P del S at constant volume, which is nothing but one of your Maxwell's relations. So similarly, starting with all these different thermodynamic potentials, you can define all the different, Maxwell's relations. For all of the cases, you have to explicitly write the differentials, compare it with the, partial derivatives, use the fact that these are all exact differentials, which do not depend on the path. Okay, it just depends on the state. And then, so the order of differentials do not matter. And then you would get back all the different Maxwell's relations. Now, you can also see one of the significance of Maxwell's relations in, directly in understanding or defining different physical phenomena. Like here you have this Clausius-Clapeyron equation, which tells you that, so here this was done for a vapor-liquid mixture, and it tells you that how does the pressure change with temperature, okay? Like the saturated vapor pressure, how does it change with temperature? And you can see that it is given as L, which is the latent heat of evaporation, divided by the temperature into the difference between the specific volumes of the vapor minus the liquid, right? So what does this tell you? So I would not go into the details of the derivations because this is something we have already discussed before. But the important point here is that now from this relation, which directly comes from the Maxwell's first relation, this expression here, the Clausius-Clapeyron equation, will tell you that, from the slope of the P versus T curve, you can say whether your, vapor phase or the liquid phase, which one has a greater specific volume or which one has greater density. And one of the implications could be to understand this phase diagram here. So here you can see this is a phase diagram for water. And here you can see that the P versus T curve has a negative slope, which again tells us why water expands on freezing, right? So you can say that, it has a negative slope. So now whatever you had done for the vapor liquid mixture, you can also have it for liquid solid mixture. And you can say that because del P del T is negative, that means your the V liquid or like V solid minus V liquid, that would be a negative quantity. And from there, you can actually say that, your for water expands on freezing, and that's the reason why you have your ice floating on water, right? So this shows how one can directly have implications of the Maxwell's relations in understanding phase transformations, or phase transitions, or understanding physical phenomena. Okay. Now there were certain questions which were very standard questions, so I will just briefly uh, recap. So we did see that if you have a certain you know for a Carnot cycle, suppose you have the PV diagram, and now if you want to write the same, describe the same Carnot cycle in the TS diagram or TP diagram, right? How do you do it? So you have to understand what are the processes involved. Okay, so this is an isothermal process as it goes along this line. Then you have an adiabatic process. Then you again have an isothermal process, and then you have an adiabatic process. So for all the isothermal processes, your temperature will remain constant, while for the adiabatic processes, your delta Q will remain constant. So that means your entropy will remain constant, right? So that means if you have to write the TS diagram, this is how it would look like. So you would have a isothermal process where temperature remains fixed. Then you have a isoentropic or like adiabatic process where your entropy remains constant. Now here you can see that your so here what happens is you're going from a higher temperature to a lower temperature. That tells you that this should be the direction of your diagram. And then you again have another isothermal process followed by an adiabatic process. This is how you can describe the same process in the TS diagram. When you're writing the TP diagram, then you have to be careful about what is happening here. So in this transition, you're going from this point to this point where your pressure is decreasing. So that's why when you write a TP, try to make the TP diagram, you have to have a curvature like this where your pressure is gradually. So your temperature is definitely reducing, but then you can see that the pressure here and the pressure here is lower, right? So the pressure lowers. Again, here the pressure increases. So the curvature of these plots would directly come from the fact as to whether you are having a compression or a expansion here, and what are the quantities that are remaining constant. So accordingly, you can redraw the same diagram, but in terms of different other thermodynamic variables. Okay, so this was one of the questions that we had initially solved, and these are very standard questions because this naturally can directly come in different competitive exams where you are given some random cyclic process and you're asked to redraw it in terms of some other variable. So then you have to use the similar concepts. Now from the differential form of internal energy, or from how you write the first law, we did see this relation. So this is a very fundamental and important relation which relates the differentials of entropy and energy with the temperature. So it tells you that dsDE is given as 1 by T. Okay, so from here, if you are suppose given a question like this where you have an S versus E plot for different processes and you are asked to tell how the temperatures for these different processes vary, then you can use this relation to actually say that wherever the dsDE slope is more, temperature will be lower. So accordingly, you can get an inequality for temperature. So this relation is a very useful and important relation that directly comes from the first law, or the differential form of internal energy. Now, there can also be questions like this where you are suppose given the free energy, okay, and you're asked to find an expression for internal energy. Now, this can also be the case where you are given the expression for enthalpy or given the expression for Gibbs free energy, right? So accordingly, you have your expressions and the relations that you'll be using will change, but the basic idea of solving these questions would still remain the same. So here what you see is, your F is given, you have to find U. So you can try to find a relation that relates F with U, and this is how you get it, right? Now here you can see that you just know F, okay, as a function of temperature, volume, and N. So now what you can therefore say is if you write U as F plus TS, you know what is the expression for F, you know what is T, that's like F is already having T involved there. So in a way, you have to write S in terms of F, right? Some derivative, something, some function of F. So for that, what you can do is you can look at the differential for the free energy, and that will definitely, so this is how the differential looks. So from here, you can say that del F del T at constant volume is nothing but minus S. So that gives you a relation of entropy in terms of partial derivative of the free energy, right? So now you can define U by this relation. So here you know F, you know T, you know the functional form of F in terms of T. So you can actually find this differential partial derivative. So you can find an expression for U. Okay. So similarly, you can just use that process to find an expression for the internal energy. Okay. Similarly, if it was some other, you are given some potential or expression for some potential, you want to find some other thermodynamic quantity, you can always proceed with this. So you can see that what are my unknowns and how you can define those unknowns in terms of the given thermodynamic potential or given variables. And for that, you have to write the differential form for that variable, like here, whatever you have written here. And then, write the unknowns as partial derivatives of your known quantities, whose functional form you know, and from there try to get the expression for the variable that you want to find. Okay, that's the basic way of solving or answering this kind of questions. Okay, and we did see that because you have different processes, which, different polytropic processes, where, for a isothermal process, that PV is given as constant for an ideal gas. But then if you have a adiabatic process, then it's given as PV to the power gamma equal to constant. So the general way would be to write a polytropic process where you say that PV to the power n is constant. Okay. Now for an isobaric process, your n will go to 0. For an isothermal process, your n will go to 1. For adiabatic process, n is equal to gamma, and for isochoric process, n goes to infinity. Because isochoric means volume is constant. Okay. So now based on these different values of n, you would get different expressions for the heat absorbed, because heat absorbed does depend on the process through which your whatever system is changing. So now from the first law, we know that dq can be written as cvdt plus pdv for a hydrostatic system. Now accordingly, you can put in the expression for pressure in terms of volume, okay, and try to do this integral. So this is how you would get the different values. So for a general n not equal to 1, this is how the expression will look like. Now for n equal to 1, you would get a log term coming in here. Okay, this is for the isothermal case. Okay. So for isobaric process, you can put n equal to 0. So this is the relation that you will get. So you can see that these are all the different expressions of heat absorbed during different processes: isobaric process, isothermal process, isochoric process, and then you have an adiabatic process where the net heat absorbed goes to 0, because that's the definition, right? For adiabatic process, there is no heat absorbed. Okay. Now one can use the Maxwell's relations also to, find relations about how different response functions vary as a function of other macroscopic variables. So suppose you want to see how the specific heat at constant volume vary with volume, or how the specific heat at constant pressure vary with pressure, right? So how do you define these quantities, right? So you can use the Maxwell's relations in that case. As you can see here, it is asked to derive this quantity, which tells us how Cv changes as a function of volume at constant temperature. And for this, you can start with this expression, okay, and differentiate both sides with respect to temperature, keeping volume constant. So this is what you will be getting. So here now what you can do is you can interchange the order of derivative, because S is an exact differential. Okay, so this is a state function. So the order of differentiation is immaterial. So this directly tells you that now del V of del S del T at constant volume, so is given as del square P del T square, right? So now you can say that if you multiply with temperature on both sides, you would get a term like TdS here, right? So That's nothing but dq. So now dq dt at constant volume is nothing but cv. So this directly tells you that del v of cv is given as T into del square P del T square at constant volume into temperature, right? So now that means if you want to see how your specific heat changes as a function of volume at a constant temperature, you can explicitly measure the double derivative of pressure with respect to temperature, keeping the volume constant, okay? And then use this relation to find how the specific heat varies. Okay, so that's how Maxwell's relations can become very handy in answering this kind of questions. Similarly, here, suppose if you're asked to find how Cp varies with pressure at a constant temperature. So again, here what you can do is you can start with this Maxwell relation, okay, and then do the same. So again, do a differentiation with respect to temperature, keeping pressure constant, and then interchange the order of differentiation. So again, here you can rewrite the term as del Cp del P at constant temperature and multiply the temperature here as well. So you get minus T del square V del T square. So now for this question, your expression for volume is given. So that means you can find the double derivative of volume with respect to temperature. Okay. And then use this relation to see how your, del Cp del P is changing. Right. So here it is telling you that del Cp del P is at a certain temperature is going as T to the power minus 4, right? So that's how one can use the Maxwell's relations to derive all these relations, okay? Now, because, we did see that, a part of our initial discussions did include the fact that as a system tries to approach equilibrium, it tries to maximize the entropy or it tries to minimize its, internal energies or potentials, like free energies or things like that. So what you can do is you can define different stability criteria, okay, in terms of this idea that you want to either maximize entropy or minimize the internal energy. So what you can do is basically this is the general, stability criteria to start with. And then based on whatever medium whatever system you're dealing with. So if you're talking about an hydrostatic system, you can put J as minus P and X as volume. Okay, so then this is your general, stability condition. And then based on whatever system you're talking about, so if you're considering a system where your number of particles are constant or a volume are constant, then you can get rid of these terms and you would be left with only this, right? And from here, you can actually, redefine and use the relations for, how, we know that suppose here for this case, we know that temperature is given as del S del E. So you can use those relations to write, new stability criteria in terms of derivatives of this different thermodynamic potentials. So this is telling you that double derivative of internal energy with respect to entropy, it always tries to maximize itself as the system tries to approach stable equilibrium, right? So these are all the different inequalities that can come out of the stability criteria. Okay, so you're getting different inequalities based on different thermodynamic potentials, and based on whatever system you're dealing with, you can choose the effective thermodynamic potential and then define whether your system is in stable equilibrium or approaching stable equilibrium or not. Right, so that's how one can define the stability criteria for a thermodynamic system. Okay, so till then we were discussing about thermodynamics, which is still the macroscopic picture. And then we gradually went towards probability because statistical mechanics is inherently probabilistic. So we wanted to have a basic idea about probability. So we started with the fundamentals. We discussed what is a random variable, what are the different, properties of any probability, right? Additivity, positivity, normalization, all of that. And then we based on different systems, we see that you can define probability density functions or cumulative probability functions, okay? And for any observable, if you know the probability density, then you can actually do this integral to find the expectation value of that function. Okay, this function is nothing but some observable. So if you want to find average of certain measurable quantity, and if you know the probability density function for the variable, which is like which you're so you have some variable x and you have some function of x, and now you want to find the average of this quantity fx. How do you do it? So you can do it in terms of this integral here, where you multiply this function with the probability density function for x and then do an integration, right? So that's your expectation value or the average value for this function. Now, there was this interesting question that we had solved. I think this was in our second or third class, where we tried to see that. So if you know the probability density function for certain random variable x, and you want to find the probability density function for another function of x, how do you do it, right? So there the idea is that there can be multiple values of x, which can give you the same value of fx. Okay, so the probability of finding fx equal to f would be given as sum of probabilities of all those values of xi, which gives f of xi equal to f, right? So from here, you could actually define this quantity here, which can give you an expression for the probability density for your function of x, right? And here, all these xi's are all the multiple solutions for the function fx going to f. Okay, so that means now if you know the probability density function for certain variable, and if you want to find the probability density function for a function of that variable, this is how you can actually do that. Okay, very interesting question. Now one can define, so when you're talking about probability in nature, you can have different kinds of probability distributions. Okay, and if you really want to, what do I say? Characterize your probability density function. You can do it in terms of certain moments, or you can define it in terms of the cumulants of the probability density function. Okay, what do you define by moment? So this is the definition. So basically, you are trying to find the expectation value of different powers of your random variable. Okay, so the nth moment would be given as the expectation value of x to the power n. Okay, it's nothing but this integral. Now here, there's an easier way of finding the moments rather than to explicitly doing this integrals. So you can define a quantity called the characteristic function, which is nothing but the Fourier transform of your probability density function. This is how it looks like. And from here, once you get the expression for your characteristic function, you can actually compare compare the coefficients of k to the power n. Okay, and the coefficients will give you the respective moments. Similarly, you can also define a cumulant generating function, which is given as logarithm of your characteristic function. And from there, by looking at, again, the coefficients of k to the power n, you can try to define the cumulants of your probability density function. Okay. And the cumulants by itself is very interesting because it describes your system. Okay. It describes the probability density function that you are dealing with. So the first cumulant is nothing but the mean. The second cumulant gives you the variance, okay, which talks about how spread out your okay. Okay, so what we are currently trying to do is we are trying to have a complete recap of whatever we have been doing all throughout this course. So we started with thermodynamics and are talking about probability, and we would gradually go towards the quantum statistics part. Okay, so okay. So now what I was talking about is that once you have so the cumulant, so the second cumulant gives you the measure of the variance, which talks about, how what's the spread of your, what do I say, whatever measures you have taken. So if you have a set of values and you have a mean for the value, now how widespread are the values around the mean? That would come from the variance, right? So that comes from the cumulant, the second cumulant. Then if you have, then there's like the third or the fourth cumulants, which talk about the kurtosis or the skewness of your probability density function. So these are all ways of characterizing or defining your probability density function. Okay, and there are also relations that directly relate the cumulants with the moments, as you can see here. So if you know the cumulants, you can write an expression for the different moments. Okay, this is how you can write them. Okay, so a simple example could be that if your probability density function is given, now what you can do is you can try to find the characteristic function, which is nothing but doing the Fourier transform. Okay. And once you do this integral, what you get an expression like this. So now you have a series of values where you have different coefficients corresponding to different, powers of k. Okay. So now you can compare this, okay, this expression with what you have here. So you can now define so if you have to find the second equivalent, okay, or so that's the variance, right? And because mean is 0, so you can directly write the second equivalent as, mean of x squared, and then you can compare it with this coefficient that you have here, and this is the value that we'll get. So this 2 is coming from here, the fact that here you have a 1 by n factorial, right? So you would have a 1 by 2 here. So when you have to balance and compare with this form of f of k, you would get an expression for uh, the second cumulative, the variance. Okay. So that's how you can compare the coefficients in the characteristic function to define the moments, and then use those moments to define your equivalence, or you can directly define or try to write an expression for the equivalent generating function, and then again compare the coefficients to get the equivalence directly. Okay. Now in nature there can be different kinds of distributions based on whatever system you're dealing with. Okay, but there are some widely well-known distributions like the normal distribution, binomial distribution, Poisson distribution. These are some of the distributions that we have discussed during our courses. Okay, so here as you can see, the normal distribution, this is the form of your normal PDF. And here you can see that it can be defined. So this tells you that now if you write the characteristic function, your normal distribution can be just defined by two, cumulants. Only the mean and the variance is sufficient, right? All other cumulants go to 0. So you just need the mean and the variance to actually define your normal distribution. Okay. You can also have discrete distributions like the binomial distribution, where you say that these are for the processes where there are two outcomes possible. Okay, so you have either sudden event happening or not happening. So you can say that the probability of that event happening is PA, and probability of the event not happening is PB. So PA plus PB becomes equal to 1. And for such a system where there are only two possibilities of either happening or not happening, and if you have n such draws, okay, you have n such events happening, and for each event you want to see now after n events what is the probability of getting a number of a events happening. So in that case you can define the distribution or the probability in terms of this term here. This directly comes from the binomial distribution of PA plus PB to the power n. Okay, that's why it gives you this form of binomial distribution. Now again here you can actually define the different cumulants. You can try to find an expression for the cumulant generating function, and this tells you, so the mean is given as n into PA. So if PA is the probability of occurrence of one event, and then if you have n such trials, then you can write the mean as n into PA, and similarly you can have the variance, which is given as n PA PB. Okay, so this is for a binomial distribution. Now, Poisson distribution is an extension of the binomial distribution where you say that you have large number of events happening, and such that in each, so what you do is there are large number of events that can happen, and then for each event, either the event happens or it doesn't happen. Okay, so in that case, basically you replace PA with P, which is the occurrence of your event, the probability of occurrence of the event given as alpha into dt, and then 1 minus alpha into dt is the probability that there is no event happening in that time window. So that is your Q, which is nothing but PB. Okay, and then you have n. So basically you have divided your entire time window into very small time segments. So you have large number of event happening, And then if you say that what is the probability that there are exactly m events happening. So in those kind of distributions, it's basically an extension of the binomial distribution itself in the limits of, n tending to infinity or dt tending to zero. Okay. And from there, you can see that this is typically how the probability density function looks like for a Poisson distribution. Okay, this is how typically when you have radioactive decays and things like that, uh, this is the typical distribution. Okay, and from here again, you can define the cumulant generating function. And interestingly, you see that for a Poisson distribution, all cumulants have the same value. Okay, so if you remember that, if you just find the first cumulant, you know that all cumulants will be the same. Okay. So these are some of the very standard distributions. You can have many other types of distributions and accordingly use the general, procedures to define the different moments or the cumulants and characterize your system. So that was about the fundamentals, or rather the basics of probability. But then as we proceeded with the course, we try to see that, okay, so there is a macroscopic description which comes in the thermodynamics, and then you have microscopic description where you look, if you have a large number of particles in a system, now each particle will have its own position, own momentum. So all this individual microscopic information, okay, that's another description, and that's a very tedious description, right? But now, how do you relate the two? What is the relation between the microscopic description and the macroscopic description, right? So there comes the statistical mechanics, which tells us that we do not actually need to have the exact detailed information about all the individual constituent particles. Okay, we do not need to know the position and momentum and everything for all the particles that are there in the system. Even if we have that information, it would not make any much sense, right? Rather, what we need is a probabilistic description. Okay, so we do not need to know all the individual microstates, but rather if we have a basic idea of what is the probability that your system stays in a certain microstate, this probabilistic description is sufficient to actually relate the microscopic picture to the macroscopic picture. And this link is what is established by the statistical mechanics. Okay. So that led us to the very concept of ensemble, which told us that now you can define your system as a macro state where you can have certain number of state functions like energy, temperature, pressure, volume, number of particles, and all of that. But the space of macro states is much smaller. And then you can have a space of microstates where you define by the individual position and momentum and of individual constituting particles. Okay, so now, and that's a very large phase space. So what you can now want to do is there's a many to one correspondence. So basically, there can be many microstates that can correspond to a single macro state. So what the ensemble theory or the concept of ensemble tells us that now if you look at one particular point in the phase space and you try to find what is the probability that you have certain number of microstates corresponding to a particular macro state within that phase space volume. Okay. So this is the definition of your phase space density, where you say that you choose a point in the phase space given as PQ, which has all, like this point corresponds to certain PQ values of all the constituting particles. Okay. And you say that at this point, around this point, if you have dn number of, microstates possible corresponding to one particular macro state that you have already fixed, and n is the total number of, microstates that you are dealing with. So then limit n tends to infinity dn by n is the phase space density. Okay, so that's how the very concept of this probabilistic approach comes in. Okay, the very concept of ensemble comes in. So you group them together. Okay, and so now what you can do is if you want to find the macroscopic value for a certain quantity. Okay, so what you can say is the macroscopic average or the ensemble average now can be written in terms of integral over the phase space volume of whatever quantity into the phase space density. Okay. because this phase space density has the information of the probability of how many particles are or how many microstates are in that range. Okay. And then you have this function, which again depends on that position in the phase space. And then you do an integral over the entire phase space that is available to you. So that will give you an ensemble average, which is nothing but the same average macroscopic value for the quantity. Okay, that's how the relation is established between the microscopic and the macroscopic picture. Okay. Now, in this regard, when you're talking about a system, which is evolving with time, so there's this important theorem that when you have a system in equilibrium and now your system is evolving, obviously the phase space density will be changing over time. How does the phase space density change? So it tells us that the phase space density behaves like an incompressible fluid, which gives us this mathematical expression, which tells us that for a ensemble which corresponds to a equilibrium macroscopic state, okay, the ensemble average must be independent of time. It should not change with time, right? The temperature should not change with time when you're talking about a system in thermal equilibrium, right? So for the ensemble averages to be independent of time, we get to this condition which tells us that the equilibrium phase space density should always be a function of the Hamiltonian. Okay. And this is a very important and fundamental relation which now tells us what could be. So for different kinds of ensembles, based on whatever system you are talking about, you can have different kinds of ensembles. But for all the different ensembles, because if you are talking about equilibrium states, then the phase space density should always be a function of your Hamiltonian. Okay. So based on that, we did discuss about different ensembles. So if you start with the microcanonical ensemble, where it's the case for a isolated closed system, okay, no exchange of energy, no exchange of number of particles, nothing. It's a closed system. So there you can define that now your energy is constant for the system. So you can say that the probability density function or the phase space density is given as 1 by omega, where omega is the total number of microstates corresponding to that particular energy. Okay. And so for microcanonical ensemble, what happens is your phase space density becomes a constant quantity when your values are within that energy range. Otherwise, it's zero. So that means now you know how to define your phase space density, and a constant will always satisfy this condition, right? Whatever be your Hamiltonian. So you can always have rho as a constant that will always satisfy this condition. So one of the solution is that, right? And accordingly, so you can define the entropy for the system as KL and omega. So basically the number of microstates is used to quantify the entropy that your system has. And if you have to write it explicitly in terms of the phase space integral, this is how it would look like. So minus K ln rho is the basic, general definition of entropy. And then in place of rho, you can put minus omega. So then it will become K ln omega, right? And this is nothing but doing this integral over the phase space volume. Now you can also move to a system where you can exchange energy. Okay, not the number of particles, but you can exchange energy where the temperature remains constant. So in that case, you can define the phase space density as e to the power minus beta h by z, where z is your partition function, which is given by this relation here. Now the partition function has all the necessary information that is required to actually describe your system or characterize your system. So once you know the partition function, you can define the free energy as f equal to minus kt ln z, and then you can use the different relations that relate the partial derivatives of f with other thermodynamic variables and use it to find the other thermodynamic variables or the equation of state and all of that. We did solve different questions based on this idea. Okay, now that you can explicitly solve for internal energy, but this is a very important relation that directly relates the partition function with the internal energy of your system. Okay. Now you can also move to an open system where you can exchange energy, particles, and everything. So then you have this additional term of mu n coming up. Okay. So that for a macrocanonical ensemble, you can see we did see that you can find a relation between the canonical partition function and the macrocanonical partition function, which is related by this expression here. So this term here is called the fugacity. Okay, again from here you can define another potential, the macrocanonical potential, which is again related to the macrocanonical partition function by this relation of minus kt ln z. Okay. Okay. Now I would not go into the details, but in order to solve for this ensemble theory questions, one of the major steps is to find the number of microstates, right? Now, when you want to find the number of microstates, often you have to start with finding a volume, okay, in the phase space. Now, for this was an important relation that we had derived. I would not go into the details, but I would just brief about the result. But the idea was that if you want to find the volume of an n-dimensional sphere of certain radius r, you can start with this, definition, do some variable transformation, take up the normal, form of v being r to the power n c n, use this well-known Gaussian integral, and then from there, what you get is this, right? So this tells you that for an n-dimensional sphere of radius r, this is the basic relation that gives you the volume. Okay, and we did use it. So when we try to solve for the number of microstates or a microcanonical ensemble, we did start by actually finding the volume in the phase space and then doing a derivative to actually look for the number of microstates. So that's how this became very handy in solving for the different what do I say, the potentials or partition functions and or the number of microstates and so on for different ensembles. So one of the questions was something like this, where we wanted to see if you have an ideal gas in a microcanonical ensemble, can you find an expression for the entropy, suppose, right? So we started with the Hamiltonian, and which governs. So the Hamiltonian gives us an information about the energy, and it governs the range of the phase space that we are allowed to cover. So based on that, we try to find the total volume in the phase space, right? So in this step, we did use this relation. Okay, so this omega here is the phase space volume, which encloses this entire region of h less than equal to E. And for this, we did actually use this relation, right? So now once you find the total phase space volume, you can do a derivative with respect to energy to find the number of microstates and then use it to find an expression for entropy. One important point that came up in this discussion when we had it during the class was the idea of indistinguishability of the particles. So if your particles are indistinguishable, then you need to consider the fact that numbering the particles or just interchanging the particles do not make any change, right? So that's why you have to divide by 1 by n factorial, which is the Gibbs factor, whenever you're talking about indistinguishable particles. Okay, so when you included the indistinguishability factor, like the Gibbs factor here, this was your expression for the entropy for the ideal gas in a microcanonical ensemble. Now one can use this to find also various other thermodynamic variables as well, right? Now one can also do the same for a canonical ensemble, where now you have to first find the partition function. So if you know the Hamiltonian, you can try to find the partition function. See, you have the 1 by n factorial coming because of the indistinguishability of the particle. Again, here, when you are trying to do this integration, you use this very idea of finding, like in order to solve for this, integral, you can use the standard Gaussian integrals as given here. So from there, you can define the canonical partition function. Okay, once you know the partition function, you can define the free energy, which is given as minus kt ln z. And based on the different, just by looking at the differential form of like writing df in terms of the other differentials, you can try to use the same expression for f to find the pressure or the entropy or the chemical potential and so on, or the internal energy. Okay, so once you know the partition function, you basically have an information about all the other different thermodynamic variables. Now for a grand canonical ensemble, because you now can exchange particles. So you do have an extra term coming in, which is the fugacity term, given as e to the power mu by kt. Okay. So there again, there's a so this is the relation that relates the canonical partition function with the grand canonical partition function. Okay. Now, once you know the canonical partition function for a non-interacting particle, you can always write z for n particles as z for one particle to the power n by n factorial if you have non-interacting particles. So accordingly, you can use those relation to write an expression for the grand canonical partition function, and then try to find the macrocanonical or grand canonical potential, which can again be related to different thermodynamic variables by this partial derivatives. Okay. And interestingly, what we saw is all these different ensembles end up to the same results when we are talking about large particle numbers. So in the classical limit, they all give us similar results. Okay. After that, so that was about our, what do I say, the ensemble theory. And then we tried to actually move towards, the matrix formulation, because that becomes very useful when we talk about quantum statistics. So we gradually tried to move towards the matrix formulation, where this idea of pure and mixed states came up. Okay, so we said that if you know exactly the state, like the exact microstate in which your system is in, then it's a pure state. Okay, which is given as, so for the pure state, the density matrix is given by this relation here, where phi is your, the matrix, or phi actually gives you the expression for the state. Okay, the state vector. Phi is the state vector. Then this outer product of phi with itself will give you the density matrix for the pure state. And if you actually don't know exactly which microstate your system is in, but you know that there are different microstates, and your system can be in different microstates with certain probabilities for each of them, then that is a mixed state. And there you can define the mixed state as mixed state density matrix as something like this. So you have different individual mixed, state vectors, each with probability rho ii. So accordingly, you can define the density operator like this. So for a system where you have the, state vector defined as something like this, it's a pure state because you exactly know which state your system is in. While if you have actually written the density vector as something like this, then it represents a mixed state. Okay. An important mathematical way of understanding or differentiating between mixed state and pure state is the fact that for a pure state, rho square is equal to rho, and trace of rho square is also equal to 1, right? Which is not the case for a mixed state. So now for any density operator like this, if you have this form, if you want to find the density matrix, like exactly find the matrix elements, you can always choose a basis. So here you can choose the basis to be plus z minus z. Okay, you can choose a basis and then try to find the individual terms by using this relation here. Okay, so this would give you all the different terms. So this is how you can actually, write the density matrix. Okay. Now, if you are asked, so once you know the density matrix, if you are asked to say whether it's a pure state or a mixed state, mathematically, you can always try to find rho square and then see if rho square is equal to rho, or if the trace of rho square is equal to 1. Like here, the trace of rho square is not equal to 1. That tells you that it's a mixed state. Okay. Now, when you define the density of density matrix, the individual matrix elements depends on whichever basis you are dealing with, right? That's true for whatever whenever you're writing describing a system using a matrix formulation. So here, suppose if your state is given by this relation here, okay, so you can very well understand that it is one microstate that your system is in. So this is already telling you that it's a pure state. Okay, but now if you want to write the density matrix in the sigma z basis, which is like the up and the down basis, what you can do is basically you can try to define your density matrix by this relation because it's a pure state. So you can do this outer product and this will give you the density matrix in the standard up-down basis. But the same matrix, now if you want to write in the sigma x basis, where the basis vectors are given by these relations here, how will you do that? So there, what we do is we always write the new basis vectors in terms of the old basis vectors. Okay. So you're writing sigma x and like up x and down x in terms of up and down vectors in the z direction. Okay. So you write the new basis vectors in terms of the old basis vectors, and you already know your density matrix in the old basis vectors. So now you can actually do this inner products. Okay. Where you have written the basis vectors, the new basis vectors in terms of the old basis vectors, and you've also written rho in terms of the old basis vectors, and then you do this product, and this gives you the individual new matrix elements. Okay. So like here, you can see that the individual, so the new matrix comes out to be something like this, which again tells you that now in this basis, you can clearly see there's only one non-zero element, which shows that again, you have a pure state. Okay. So based on whatever basis vectors you choose, your matrix elements would vary. But the basic idea, so the fact that you have a pure state can be directly understood from the fact that you are clearly defining the system in terms of one microstate. Okay, that by itself is already telling you that it's a pure state. Or if you have rho, you can always find rho square and see the trace of rho square going to 1. That will already tell you that it's a pure state. Okay. Now, if you want to okay. So if you want to find the expectation value for different quantities, what do? So you multiply uh, the function, multiply the matrix for your, like the density matrix with the matrix for the observable that you want to find. Okay. Like for this case, you know the matrix for your sigma x. So now you want to find the mean along the mean speed along the x-axis. So what you do is you multiply sx with rho, okay, and then take a trace of that matrix, right? That gives you the mean speed in the x direction. Similarly, you can do the same for the sz as well. Okay. So that was about the mixed and the pure states and how you define the different matrix elements based on whatever basis vectors that we can choose. So once we had discussed about the density matrix formulation, we gradually went towards quantum statistics. Okay, so this is something which we had discussed at the towards the end of our course. So it's a comparatively recent topic that we have discussed. So I would go a little fast in this section. So here, the very idea is that when you're talking about, quantum mechanical, microcanonical ensemble or whatever ensemble you want to talk about, when you're talking about quantum mechanical system, you are talking about the fact that now your energy states would be, quantized. Okay, so you can have different energy levels with different degeneracies, and then you have indistinguishable particles which can be put into all these different energy states. Okay, so the basic idea was that based on what kind of particle you're talking about, whether your particles are distinguishable, whether they're indistinguishable, whether these particles can be represented by symmetric wave functions or antisymmetric wave functions. Based on all this criteria, the grouping of the particles into different available energy states would vary. Okay, so the distribution of particles into the different energy states would depend on what kind of particle we are talking about, and that will govern how many ways in which you can do this distribution, right? And this how many ways is nothing but what would govern the number of microstates. Okay, so if you're talking about a microcanonical ensemble, and if you want to find the total number of microstates, okay, and then if you want to find the most probable distribution, which gives you the maximum number of microstates, okay, so you can start with a general formulation where you say that, you have a system, you know the total number of particles. So this is how, so whatever distributions you have into different energy states, summation over I Ni should go to the N is the total number of particles. And then you know the total energy. So summation over I Ni epsilon I should go to the total energy of the system. And then while these two conditions are satisfied, now you can have different ways of grouping your particles into all these different energy states with different degeneracies given as G1, G2, G3, G4. So for each distribution set, there are certain, so distribution set means how are you grouping your variables, right? How are you grouping your particles? N1 particles in epsilon 1 state, N2 particles in epsilon 2 state, right? This grouping, if you define it as a certain distribution set, for each such distribution set, you would have certain number of ways of doing it. And then you can have different distribution sets associated with the same macro state, right? So summation over all such possible distribution sets, okay, and like the probabilities of doing all such distributions would give you the total number of microstates, okay. And for each distribution, now you can define the number of ways of achieving that distribution as product of how many ways can you group N1 particles in this state, N2 particles in this state. So that again would depend on what kind of particles you are dealing with. So now for a, you know, uh, Bose-Einstein case where you can have as many number of particles in as many number of states. So even in a single state, you can put all the particles. There's no restriction to that. So there you can group the particles according to this relation here. So this gives you the total number of ways of getting a certain distribution set. This would vary from the Fermi-Dirac case where you can either have one particle or no particle, right? So there the number of ways is given by this relation here. Similarly, for a classical particle where the particles are distinguishable, okay, there the number of ways is given by this relation here. So now based on this, so this W is like a weight factor which tells us how many ways can you achieve a certain distribution set, okay. So now summation over all such possible distribution sets would give you the total number of microstates, omega. So S would be given as K ln omega. Now at this point, we did look into the distribution that gives us a maximum number of, um, possibilities, like maximum number of omega. So from there, in like by maximizing this value here, okay, we would see that this is the general form that we get, okay. So from there, we could define the most probable value of N for a certain energy level. And this is the general form where based on whatever particle we are dealing with, your A value would change. So for a boson, you would have A as -1. For a Fermi-Dirac, you will have A as 1. For a classical Maxwell-Boltzmann particle, your A would go to 0. So based on whatever particle you are dealing with, you can define the most probable value of N, okay, for a certain energy level using this relation. Now, using that, you can actually again put it in the expression for the entropy. And from there, you can try to now relate this number distribution, right? This whatever ways you were grouping your particles and this entire distribution and how many ways you can do that. So this entire counting of microstates, now you can relate it to macroscopic variables like, pressure, temperature, entropy, and so on. Okay. Now, if you remember in the grand canonical ensemble, we had PV by KT given as ln Z, where Z was your grand canonical partition function. So now you can actually use this relation to, define the, number distributions to thermodynamic variables. Okay. So similarly, now if you want to do it for a canonical ensemble, you have to find the canonical partition function. Okay. You can always, so this is the value that you have to find, right? This summation is the partition function. But again, here you can now put the fact that in whatever ways you are trying to achieve your macro state, there are certain number of microstates associated with it. And based on whatever particle you are dealing with, this number of microstates would vary, right? So the statistical weight factor would take into account takes into account whatever kind of particles. Based on whatever particle we are talking about, we can 1 second, just 1 second. Okay, so uh, what I was talking about is, so now based on whatever particles we are dealing with, the number of ways of achieving like uh, a certain macro state would vary, right? So accordingly, your this factor here, like which takes into account the statistical weight factor for a certain distribution, would change, right? And you can put in these values based on whether you have a boson or a fermion or a classical particle. Okay, so this G here is nothing but WNI that we had initially found. Okay, and now based on whatever system you're talking about, you can put in those values to actually find and evaluate the canonical partition function, but now from the number distribution, from by using the fact that different particles get distributed into the energy states differently. Okay, so now for a we did solve for all the different cases. Okay, so if you start with the Maxwell-Boltzmann, the distinguishable particle case, you would see that you would get an expression like this. Okay, this is how you can relate the canonical partition function with the partition function for one particle if you have non-interacting particles. Okay, and then once you know the expression for the canonical partition function, you can see that this is same as what you had done also for the classical treatment that we had initially done, right? And from here, now you can actually just include the fugacity term to get the grand canonical partition function. Okay, so that's how you can define the different, you know, canonical partition functions for distinguishable particles. So basically, you have just put in the value of G in epsilon, which is the number of ways of achieving a certain distribution set. Okay, using the fact that total energy can be written as summation over NE into the individual energy level energies. Okay, and then rearranging the terms that directly gives you this expression. Okay, now for the indistinguishable particles like the Bose gas or like the bosons and the fermions, okay, based on whatever particle we choose, our number of ways of putting particle in a state would differ, right? For a Bose gas, your n epsilon can take any values from like 0, 1, 2, whatever, while for a Fermi Dirac, you only have n epsilon values go between 0 and 1. Okay, so accordingly, you can rewrite this. So there are two summations involved. Now you can actually write these two summations as a product of multiple terms where n naught, ni, all these values can either take 0 or 1 for the fermions, or it can take all possible values starting from 0 for the bosons. So accordingly, if you do that, you would get an expression for the grand canonical partition function for the Bose-Einstein case or the Fermi-Dirac case. And from there, once you know Q, which is the grand canonical partition function, you can define the Q potential and then also relate it to thermodynamic pressure or the other thermodynamic variables using this relation. This is a general relation for all the three cases together. Based on whatever particle, you can put the value of A accordingly. Okay, and then what we did next is now we took up individual cases for different values of A. Okay, the Fermi-Dirac case and the Bose-Einstein case, and from Q or from the expression of pressure, we tried to define the other thermodynamic variables, tried to see what happens at certain, low temperature limit, high temperature limit, and all of that, right? So you can define the average number of particles or average energy by using these relations. And here, when you define the average number of particles, this term here gives you the mean occupation number. Okay, so This again is a measure of how different the number distribution is for the different particles. Okay, so for a fermion, this is always less than 1. For a boson, as you can see, as you know, epsilon minus mu tends to 0. So here you can see that this diverges, which again hints at the condition of Bose-Einstein for condensation. And then this is for the third case is for the Maxwell-Boltzmann classical particle. So you can start with this, and now considering that you have a large volume where the energy levels are quite, close, you can actually change from a summation to an integration, and this is how it would look like. Now, for this case, what is important is, so now you are writing P in terms of this integral, which is telling you that based on your system, okay, there are two things. First is whatever dimensions you're dealing with, okay, that would govern whether what kind of phase space volume expression you would have, and based on the energy dispersion relation, so how energy is related to momentum and so on. So this too would govern the type of expression that you would have for uh, pressure and the different thermodynamic variables. So if you talk about non-relativistic particles where energy is given as p square by 2m, so free non-relativistic particles in a 3 dimension, then you would see that you would get this relation between pressure and energy, which is true. Now, when you have a relativistic particle, this changes to 1 by 3 E by V, which is coming from the fact that the dispersion relation that relates energy with momentum is different when you have a relativistic particle. Okay. So like this, you can define all the different, thermodynamic variables. Till now, we have not replaced the value of A. So this is a general relation. Okay. Now, for a Fermi-Dirac case, you now put the value of A as 1. Okay. And try to solve for the total number of particles, what is the expression for the total number of particles. So you can get an expression for a density of states where you can see that it goes as epsilon to the power half when we are talking about a 3-dimensional Fermi-Dirac case. Now, based on if your system is in some other dimension, this value would accordingly change, right? So here you can define this quantity. This integral can be defined as f of nu z. And accordingly, you can define an expression for the number density or the pressure and so on. Okay. So here you can look at the high temperature, low density limit, or you can look at the high density, low temperature limit. Okay. So the low density, high temperature limit is nothing but the classical limit, where you can see that you get back the same classical results. Okay. While at low temperatures, what happens is that your T tends to 0. So n lambda cube by G, this tends to infinity. So here, if you look at the mean occupation number, this is how the mean occupation number looks like. So there is a threshold, okay, below which your n epsilon is 1, above which it's 0. So now your integral, which was initially from 0 to infinity, now the limit changes from 0 to EF, which is your Fermi energy. Okay. And if you do these calculations, what you see is that the Fermi energy is a function of the number density. Okay. And if you use the relation between the energy and pressure, you can also see how pressure is related to number density. Okay. And that's how you can define for. So when you are using this relation, okay, 2 by 3 E naught by V, you're actually considering non-relativistic particles. Okay. If it is a relativistic particle, this expression should change. Now, there's this important, quantity n lambda cube, which actually gives us a, quantification of when quantum effects become dominant. Okay. So if n lambda cube tends to 0, which is like the low density, high temperature limit, there we are towards the classical limit. While when n lambda cube becomes comparable to 1, we are actually in the quantum limit. Okay. Now, again, you can now put A as -1, okay, and then look at the ideal Bose gas, the same expression, but now with A set as -1. So here again, we see that for n to be defined, there is a maximum value of Z. There is a limit to what your chemical potential can be. So your chemical potential should always be lower than the ground state energy. Okay. And that sets the limit to the fugacity value as well. So your value ranges from 0 to 1. Okay. And then you can again go from summation to integration, considering that you have a large volume and the single particle states are continuous. Again, you can use the fact that, so see, this relation is a general relation. Okay. Now you put A as -1 for the Bose gas, and based on whatever your dispersion relation is, and here we have already considered the 3-dimension because you have 4 pi p squared dp. So this is for a 3-dimensional case. For 2-dimension, your volume calculation would vary. So accordingly, you get an expression for pressure. Okay. And then whether you have a non-relativistic free particle or a relativistic one, your expressions for density of states will also change. So for a 3-dimensional case, for a non-relativistic free particle, you have a density of state which goes as epsilon to the power half. Okay. And here there was an important point which was different between the Fermi-Dirac case and the Bose-Einstein case, where because in a Bose gas, you can always put, you don't have a limit to how many number of particles you can put in the ground state. You have to explicitly consider the fact that there is a sufficient and a significant amount of chance that you have particles going to the epsilon equal to 0 state, which is not explicitly considered here in this density of state. Okay. So that's why when you deal with Bose gas, you have to explicitly write for the case where your epsilon is set to 0. Okay. Because otherwise this density of state would give a 0 weightage to 0 energy, which is not true. So explicitly, while you write the expression for pressure or number of particles, you have this extra term which is coming because to consider the 0 energy state. And from there, you can actually get an expression for pressure, number of particles. Again, you get this integral, which you can write as the Bose-Einstein function, which is nothing but a series of z. And because z can lie between 0 to 1, that means you have a maximum value for this function as well. Okay. You can also define an expression for the internal energy, which is given by this relation here. Now, because you have an upper limit to the value of z, you have an upper limit to the value of g, or the Bose-Einstein function, and therefore there's a limit to Ne, which is the number of particles in the excited state. So this tells us that if your number of particles exceeds a certain value, then the particles will start accumulating in the ground state. Okay, and that's the condition where your Bose-Einstein condensation sets in. Okay. So for n greater than Ne, you would have this many number of particles in the excited state, but whatever extra particles you have, they would go and get start filling up the ground state, which is given as n naught. Okay, and that's the condensation. So depending on this expression, you can actually find a relation for the critical temperature below which condensation starts happening. And this is just coming from the fact that, mathematically, if you have to look at it, this comes from the fact that your Bose-Einstein function has a maximum value because Z has a maximum value of 1. Okay. So when temperature goes below the critical temperature, you have a normal phase for particles in the excited state, and then you have a condensed phase for particles accumulating in the ground state. Okay. And when the condensation happens, you have to put Z becomes 1. Okay. And your number of particles start accumulating in the 0 state. So this is how Ne and N naught would look like. Okay. And again, based on whether you are below Tc or above Tc, you can get expressions for pressure. Okay. This is how it would look like. So here you can see it goes as T to the power 5 by 2 when T is less than Tc. For T greater than Tc, it would go as here it's like T into G 5 by 2, G 3 by 2. So similarly, you can define an expression for internal energy, and also, so once you know the internal energy, you can define specific heats. Okay, and also look at how they vary with temperature below the critical temperature, above the critical temperature. Okay, and interestingly, you see that the value approaches at high temperatures, value approaches the classical value, but from a higher value. So at the critical point, the specific heat value is higher than the classical value of 1.5. Okay. this was an important relation that came out of this question, which tells us that what is the condition when Bose-Einstein condensation can happen. So given a certain dispersion relation where energy goes as ak to the power s, okay, and if the dimension is given as d, then d by s should always be greater than 1. This comes from the fact that your expression for Ne should be defined if you have Bose-Einstein condensation, right? So that tells us that given a certain dispersion relation and the number of dimensions, if d by s is greater than 1, only then the condensation will occur. Okay. That also tells you that for massive bosons, where E goes as p square by 2m, BEC happens only for 3 dimension, not in 2D or 1D, while for massless bosons, because energy is given as P into C, Bose-Einstein condensation can happen in 3D as well as 2D, though not in 1D. Okay. Uh, we talked about ideal Bose gas. We also talked about harmonically trapped Bose gas. This is something we had discussed in the last class itself. So there you can see that now, because you are in a harmonic potential, your energy levels are given by this relation here. So accordingly, if you have to find the number of states between some energy 0 to epsilon, this is how you have to do it. Okay. So from there, again, you can define the density of states. Now, once you have a density of state, you can always define this summation, which is nothing but integration of this term here. So you're actually now doing an integration with respect to energy, okay, considering the density of states. And similarly, you can try to find the total number of particles. And once you get the expression for n, you can always say that once you know n, you know that there is a maximum value of n that one can have, which would set the critical value beyond which condensation would start. Okay, so whenever you have a well-defined expression for n, you can relate it to, rewrite it in terms of the critical temperature and get an expression for the critical temperature and say where the condensation starts to fall. Okay. Similarly, so again, you could get all these conditions of what happens below the critical temperature and above the critical temperature. Okay, whenever you're below critical temperature, you have to set Z as 1. Okay. And again, interestingly here, we did see a discontinuity in the specific heat, as you can see here in this plot. Okay. So for a general treatment, you can always start with a general dispersion relation, okay, or a general density of state expression like this, and then try to find an expression for n and look at the two conditions, okay, less than Tc and above or greater than Tc. And if less than Tc, if you can put z tending to 1, where the Bose-Einstein function becomes equal to the zeta function, you get an expression for the maximum number of particles that can be there in the excited state. And from there, you can define an expression for critical temperature. So this is like the general expression for any Bose gas. Okay. And you can use the same concept to define energy or, specific heat and so on. So again, here, when you write this expression, you can see, for T much greater than Tc, you are in the classical limit. But these individual terms tell you how you are deviating from the classical picture. Okay. Again, for Cv, you have this additional terms, which tells you that in the high temperature limit, it approaches the classical value, but from a higher value. So at the critical point, your specific heat is larger than what is expected in the classical limit. So these were some of the cases that we had discussed. So similar treatments, but giving different results, describing different phenomena um, based on what are our dispersion relations, what is the dimension, what are the type of particles that you're dealing with. Our expressions change, while the basic protocol of the basic treatment remains similar. And that's how we actually talked about the different quantum statistical systems. Okay. So that was about this entire course, starting from thermodynamics to probability to ensemble theory to density matrix and then to quantum statistics. So that was about this course. I think that's all for today. Hope this was helpful. Yeah. Thank you.